We're going to talk about Module 11. Now, I had you look over my video on subnetting using classful subnetting. I'm going to actually do a meeting from probably in your office, Caleb, on Thursday, so I can actually do that on the whiteboard in there, our big screen.
Okay.
So we'll do that, and because I can't really draw zeros and ones, but I'm going to show you how the curriculum teaches it, and we'll talk about IPv4 addressing. We talked about 32-bit addresses, and we talked about what an IP address is. We talked about the different classes of addresses. So this is just review, but we talked about how last week every IP address has at least two portions, and that is a network portion and a host portion. And we discussed a possible third portion, and that was the subnetwork portion. So we'll talk about subnetting and what subnetting is after this short review on IPv4 addresses. Now, do be aware this is IPv4. So they're 32-bit addresses consisting of 4 octets, so 4 sets of 8, which is 32 bits. Each one of them has an IP address with a corresponding mask. And remember, the mask is used to determine what portion of an address is the network portion and what portion is the host. We were discussing last week that in a subnet mask, we put ones in the portion of the address or the mask that is network portions and zeros in the host portion. So even if I just gave you this and did not tell you anything else, I said, this is the mask for an IPv4 address. You could tell me that the first 2 octets are the network portion and the last 2 octets are the host portion, because there are zeros in the mask wherever the host portion is, and there are ones in the mask wherever there is the network bits. So for instance, if I look at this address right here that's been assigned on this PC, 192.168.10.10, and the subnet mask of 255.255.255.0, this tells me that this particular machine is actually on the network 192.168.10.0, all right? And it is the host .10, all right, because of this mask right here, this 255.255.255.0. Very important concept. The mask helps you know what portion is the network portion and what portion is the host portion. So again, here it is in binary. Anywhere there's a 1, that is the network portion. Anywhere there's a 0, host portion. Now, one of the neat things that actually goes on that people don't realize is every time a machine pings or attaches to or connects to another IP address, the first thing it does is it takes its currently configured IP address and ANDs it to the subnet mask. Now, ANDing is a logical mathematical computation. And basically it works like this. If you put a 1 to 1 together, you get a 1. Anything else and you get 0. So if I took this mask that was assigned in this IP address, 192.168.10.10, I convert it to binary and AND it, you will see what happens is that when it falls through, the only thing that falls through is 192.168.10.0. So before the host that has, way up here, the host that has this IP address assigned to it, before it can ping anything else or connect to a web server or anything else, it first takes its IP address and its mask and it ANDs it to determine what network it is sitting on. And so this machine now knows that it's sitting on the 192.168.10.0 network. It then takes the destination network, and I'm gonna do this real quick. Now let's imagine that this host 192.168.10.10 is sending something to a host of 10.1.1. Well, let's do 1.1. Okay, and I'm doing that for simplicity's sake. So you know that when this host went to do the ping to this particular address, it first ANDed its address and figured out I am on the 10.0 network. It then takes the destination IP address and converts it. So 128.64.32.16.8.4.21. Okay, so this is basically 10. 1 is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. One too many. I say I may have too little here. Nope, that's right. And then we're going to do 1 again. 1, 2, 3, 4, 5, 6, 7, 8. And 1 again. 1, 2, 3, 4, 5, 6, 7, 8. So 10, 1, 1, 1 in binary is that. This host, the 192.168.10.10 host, would then take its mask and AND it to the destination that it is going to be pinging. And what's going to happen is what falls through is very different. Okay, so what falls through is 0, 0, 0, 0, 1, 0, 1, 0, dot 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So what fell through was 10.1.1.0. So now the host 192.168.10.10 knows the destination 10.1.1.1 host is not on the same network as it. And what it will do is it will turn back around and will send it to this default gateway, which is a router. We talked about path determination last time. And that router has to see if it's got a route to the 10.1.1.0 network. Now let's imagine that this host is actually going to ping, instead of 10.1.1.1, it's got to ping 192.168.10.11. Okay. And so what we can do here is we can do 1, 2, 3, 4, 5, 6, 7, 8 dot 1010100, which is 168, 1, 2, 3, 4, 1010 dot 1, 2, 3, 4, 1011, which is 11. Now watch what happens. A very different thing happens when it ANDs. If 192.168.10.10 pings 192.168.10.11, it'll figure out that it is on the 10.0 network. It will then AND the destination, and guess what falls through? You'll see that what falls through is, in fact, I know there's one of these goes. What falls through is 192.168.10.0. So if 192.168.10.10 pings 192.168.10.11 with a /24 mask, by the way, that's what's on this host, it will know that it's on the same network and it will send it directly to it. It will actually do an ARP request, ARP reply, and then it will send that ping across. So it's amazing how quickly two hosts can ping one another, because every time they do it, they go through and figure out what network they are on, what network the destination is on, and then look in that local host route, remember the host route table we talked about last week, and determine where to send the ping or the web connection request or any of those. Are there any questions about this? Because this is amazing how it actually works. Okay. Now, one thing I do want to talk a little bit about is, remember, since if we have the network, in this case, we have a network of 192.168.10.0/24. That means the mask, by the way, 24 just means there's 24 ones. So the mask is 255, 255. Oops, sorry, y'all. I'm typing with my bad arm, trying to use it a little bit, and it's not working great. Okay, so with that mask, we know that this address, 192.168.12.0, cannot be placed on a host because that is the network ID. The first usable IP address in this network would be not 12, it would be 10. 12 is my favorite, so sometimes I accidentally type 12 and I should be using a different one. 12, 10.1 to 192.168.10.254. Those are your usable addresses. Okay, tab that in there. And then the broadcast for this network is actually, what would it be? What would be the broadcast for this network? Remember what we talked about last week? We said if there's all zeros in the host portion, that's the network ID. If there's all what in the host portion, you get your broadcast ID.
255.
It'd be 255. So if there's all ones in the host portion of an IP address, this is the broadcast, and this is the network. And then every one of these down here, these are usable addresses. So everything from 10.1 to 10.254 with a /24 mask are usable. So we can assign those to a host. That's what this video goes over, folks. And that's what is being talked about here. The idea of the usable addresses, the network address being the 10.0 because all the host bits are zeros. Usable addresses are anywhere the host bits are not all ones or all zeros. And anywhere the host bits are all ones, that is the broadcast for that particular network. So let's look at another example. Let's do this. Let's take 10.0.0.0/16, not 15. We could do 15, but let's do 16, make it a little simpler. So what is our mask in decimal?
255.255.0.0.
Okay. So what would be, so all's here right now. Matthew, what would be our network ID for this particular?
10.0.0.0.1.
10.0.0.0 would be our network ID. That's our network ID. Okay. So Matthew, what would be our first usable IP address?
10.0.0.1.
And our last usable would be 10.0.255.254. And then our broadcast, what would it be? 10.0.255.255. So when there's all zeros in the host portions, that's the network. Okay, folks, y'all have to forgive me for 1 second. I've got to step away. I'm very sorry about that, folks. My upstairs toilet's acting really weird. It's like it won't fill up with water, and then suddenly it'll start filling up with water. And I'm trying to figure out, I actually thought my well had died yesterday. It scared me to death. But it's just started making noises. I want to make sure it wasn't in there running over. But so that is our network. And then down here with the /16, where there's all ones in those 2 octets, you've got your broadcast. Then anything inside of here is in fact usable. And that's always confusing because people go, well, so you're telling me that 10.0.0.255 is a usable address. And I'm saying, as long as the mask is /16, the answer is yes. Because this octet may be all ones, but this one is not all ones. So you have to look at both octets of host bits. They're not all ones. They're not all zeros. That's a valid IP address to put on a host. And that's what they're trying to get through here in this particular section, is the concept of the network ID. If you are ever asked what is the network ID on an IP address, all you have to do, by the way, the easiest way to find it, if you go 192.168. Well, let me make it simpler because I'm lazy. Let's do 10.1.1.33/27. Okay. And you don't know a whole lot about this yet, but if anyone said, tell me what the network ID is for this particular IP address, the simplest way to do it is just to AND it to its mask. So what is the mask /27? Anybody? You know, it's 255.255. And then 27 would be, by the way, that's 24 ones. You just do 1, 2, 3, 4, 5, 6, 7, 8. And that, by the way, when you convert it, is 224. Do I need to go back and do the whole section on conversion from decimal to binary and binary to decimal?
I'd help a little bit.
Okay, we'll go back and do that. I'll go back and do that next week. But well, let me show you right now what we got here. So we need to find out what network this IP address is on. It's really simple. Convert to binary. 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Wait, that's 5, 6, 7, 8. Wish I had $1 for every 1 and 0 I've either typed or put on a board. I'd be so rich. Actually, I wouldn't be that rich, but it'd be all right. 128, 64, 32, 16, 8, 4, 2, 1. That's 33. Okay. Now, /27 is 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Now we ANDed these together just like we're a host, and we're going to get our network. 1, 2, 3, 4, 5, 6, 7, 8. Oops. Which tells you that this is the network 10.1.1.32 /27. So if you ever need to know what network you're on, simply convert to binary and then AND it to the mask that is associated with the IP address. And that will give you your network. All right, I'm gonna back up. I'm gonna back up and punt here for a second. Let's talk about binary. I thought we might be able to just go past this, but we're not going to do it. So let's talk about binary and what binary is. Binary is a base 2 numbering system. Okay, so one of the things that we need to think about is right now we use what is known as a base 10 numbering system. All right, so just for why do we use a base 10 numbering system? Even though my fingers are kind of fading in and out here. We do it because we got 10 fingers. Okay, so we got 10 fingers, we use a base 10 numbering system. Now you really don't think about this much, but if you have $110 in your pocket, what you really have is the following. You have 10, all right, you have hundreds, there's a hundreds position. Okay, there's a tens position and there's a zeros position. So 10 to the 0, 10 to the 1, and 10 to the 2. And what you really have here when you have $110 is you have 1, 100, 110, and no zeros for $110. If you had 115, or you have 115, even if it's, you have 5 ones, 110, 1 100. So powers of 10, we already know. We use this every single day. We don't even think about it. We have, when you think about a base 10 numbering system, you've got 0 to 9 as your positional numbers. Okay. So in other words, I can go in here, and if I had 9 in the hundreds position, I'd be doing a whole lot better than I am right now in my bank account. Now, I am a state worker, so you know it's mid-month. We're getting toward the end of the month, so we're paid once a month. You know how that is. So 915 if I had 9 100s, 110, and 5 ones. Well, the base 2 numbering system, I tell people all the time, computers are dumb as bricks. You can either have a 0, which is off, or you can have a 1, which is on. And in base 2, we got this down there, in base 2, you either turn a position on or you turn it off. Now again, here's an example of base 10, 10 to the 0s, the 1s, 10 to the 1s, 10 to the 2s, 10 to the 3s. So if you had 1,234, you'd have 1, 1,000, 2 100s, 3 10s, and 4 1s. Binary uses 2 to the 0 with a positional value of 1, 2, 4, 8, 16, 32, 64, 128. By the way, 2 to the 8th is 256, then 512. And when I tell you one thing I do, folks, when I sit down and take a Cisco test, one of the first things I do, you get this little grease sheet you can write on. I do, 2 to the 0 all the way up through, and it's hard for me to do here because I don't have my thing. 0 equals 1, 2 to 2. I actually write down all the way to like 2 to the 12th power on that sheet so that I don't make any dumb mistakes with conversions. But we see here, if we have binary number 11000000, you convert this binary to decimal with what's called the addition method. You go in and look and say, okay, I've got 128. So I take 128. That position is turned on. 64 is turned on, so I add 64 to it. None of the other bit positions are turned on, so those are all zeros. And so 11000000 is the decimal number 192. So it's called the additional or added or addition method. So if we had this particular IP address, all you have to do is look at what's turned on. We've done 192 already. Here's 168. So we take 168 and we go, 128 is turned on. So that's 128 plus 64 position here is not turned on. See that right there? It's off. So we don't add it. The 32 position is turned on. So we add it. 16 is not turned on. 8 is turned on. And then nothing else is turned on. And that, when you add it together, gives you 168. We move on down and we see same thing here. 8, 2, and 1 are turned on. So that's 11. And then go on down and you get 10 down here. Now, one of the things I try to teach my students and that would be good for you to learn are the following. If it's all zeros, you know the value is going to be 0, right? If it's 1, 2, 3, 4, 5, 6, 7, 8. 128 is the only position turned on, so 128 is the value. If it's 1, 2, 3, 4, 5, 6, 7, 8. It's 128 plus 64, which is 192. 1, 2, 3, 4, 5, 6, 7, 8 equals 224. 1, 2, 3, 4, 5, 6, 7, 8 equals 240. 1, 2, 3, 4, 5, 6, 7, 8 equals 248. 1, 2, 3, 4, 5, 6, 7, 8 equals 252. 1, 2, 3, 4, 5, 6, 7, 8 equals 254. And then 1, 2, 3, 4, 5, 6, 7, 8 equals 255. So if you look at an octet, so one set of 8 bits, the lowest number you can have is a 0, the highest number you can have is a 255. Now, the reason I teach my students to learn these is because imagine I give you this binary number, 1, 2, 3, 4, 5, 6, 7, 8. 8. You should very quickly be able to say that's 193 because the first 2 turned on is 192 plus 1 because this is a 2 to the 0 position. Okay, so that equals 193. I'll show you another trick. Anytime, even if you didn't know what this was, make sure I got enough. 1, 2, 3, 4, 5, 6, 7, 8. Is that an odd or an even number?
Even.
It's going to be even because the ones position is turned off. So anytime you see the ones position turned on, that's an odd number. Anytime it's turned off, it is an even number. Now we can look right here and say, okay, this is 240 plus 8, excuse me, plus 4, 244, 246. I believe that is correct. 124, yep, 246. So you can see by learning these breakdowns here, you can convert fairly quickly. But if you don't know, okay, again, if you don't know, use the additive method. So I could very easily have done this. I could say, okay, the 128 position is turned on, plus the 64 position is turned on, the 32 position is turned on, the 16 is turned on. All right. The 8 position is not turned on, the 4 is turned on, the 2 is turned on, and the 1 is not turned on. Equals 246. So converting from binary to decimal, use the addition method. Now, what if you want to go to the other way? Now, I will show you this though, real cool. Here's an activity. And folks, you can do, this is right here. See, this is going to be 7. We know that all zeros and 111, this is 7. So we check it. Correct. New number. So if you need practice, it will just keep spitting numbers out at you. You can just continue to put numbers in here. If you put the wrong thing in, it tells you it's wrong. And you can keep trying again. Okay. So this activity is excellent for you and your students. Now let's imagine we want to go the other way. Let's say we want to convert from a decimal number to binary. We use the subtraction method with decimal to binary conversion. So let's take this and look at this. Let's say I'm going to give you the number just right now. Let's say 192 in decimal. We want to make it binary. First off, we say, okay, can I subtract 128 from 192? The answer is yes. So we're going to take this, we're going to subtract it, and what's left over? 64 is left over, right? So we're going to go down here in our thing. We're going to turn on the 128 position. We're going to say, can I subtract 64 from 64? The answer is yes, with a remainder of 0. So at this point now, we go down here and say, okay, we're going to turn on the 64 position, and then everything else be 0. So we just converted 192 to binary using the subtraction method. What if it was this though? What if it was just 100? Or let's just do just 64, okay? We would say, can I subtract 128 from 64? The answer would be no. So we come down here and in the 128 position, put a 0. Then we say, can I subtract 64 from 64? The answer would be yes. So we turn on that and we're left with a 0. So we just put in zeros for the rest of the bit positions. Okay. 1, 2, 3, 4, 5, 6, 7. Had one too many. There we go. Yep. Okay. So the decimal to binary, you use the subtraction method. So you say, can I subtract it? If yes, put a 1. If no, put a 0. Same thing. You keep going. So here's our example. So let's say 192. Again, yes, we can subtract a 1. So we put that position in. Same thing here. So we just go through and that's that number. Now 168. Can I subtract 128? Yes, I can. Okay. So we subtract it and we end up with 40 left over. Can I subtract 64 from that? The answer is no, so put a 0. Can I subtract 32 from it? The answer is yes, with a remainder of 8. Put a 1. And so on and so forth until you convert it to 10101000. And that is the method. So we use the subtraction method to go from decimal to binary, and the addition method to go from binary to decimal. Questions? Okay. By the way, just for poops and grins, I will tell you this. I know this is an octet, 1, 2, 3, 4, 5, 6, 7, 8. It's also typically called a byte because it's 8 bits. Each part of this, every 4 bits is actually considered a nibble. And I know that's crazy, but they do call 4 bits a nibble, 8 bits a byte. All right. So, and our IP addresses are 4 8-bit octets, so we get up to 32 bits. Questions about these conversions? There's a good activity here, 238. You can just subtract it, and you can just keep doing new numbers. So 0, 1, which I believe 16, 17, 26, 0, 1, 1, 0, 1, 0. Yep. And I just did the subtraction there real quickly. I did 64 and then 16, 8, 4, 2. And that's it. So pretty neat little thing. I do want to touch briefly on hexadecimal because we will be seeing that in IPv6 addresses. Hexadecimal is a base 16 number system. We use it because IPv6 addresses are so big. And so it actually, since it's base 16, we can't just use the digits 0 to 9 because we've got to account for 10, 11, 12, 13, 14, and 15. So we've got A through F. A signifies 10, F signifies 15. You also see the binary equivalents in hexadecimal. So you'll notice that hexadecimal F is 1111 or 15 in decimal. When we get in IPv6, you will notice that we're going to be talking about hextets instead of octets or octets. We talk about hextets, and that is this 16 binary digits or 4 hexadecimal digits, which gives you an enormous number of IP addresses. Again, remember 340 undecillion addresses. Enough for every grain of sand on the planet. Does that review help you with what we were just going through, folks? Going back through that.
Yes.
Good, good. Okay. Again, don't forget you've got plenty of practice in this section. You can do as many of those practice items as you want by looking at the activity 519, and activity 516. Those will allow you to practice as much as you want. There's also a neat little thing out there called the subnetting. It's called the IP address and subnetting workbook. And a lot of people always look for the answers because students want to cheat. But there's actually this big workbook here that goes through IP addressing. This does have all the answers in it, but if you want to give this to your students, it's tons of conversions they can do. And then there's the answer sheets. And again, you can get them without the answer sheets. So this is the one without the answers. Well, that's not, but there is one without the answers. So I have to look student version. Let's do the student version. Just be aware if you assign this to your students, they will cheat and go find the version that has all the answers in it. So maybe something you want to have them do in class so that you can verify it. Or if you really want to be sneaky, what you do is you go in and you open it up in Acrobat and you change these, change it, and then give it to them. And then all their answers will be wrong. I know that's evil, but it's fun. Okay. So also for you, again, you can go out there and get this IP address in the Subnetting Workbook version 2.0, and there's plenty of places for you to test your binary to decimal and decimal to binary conversion. Okay, any questions? Okay, so let's go back down right here. Again, doing our ANDing, so we know now about the conversion and all those. Let's talk a second about the types of IP addresses. In IPv4, there are three main types of addresses. There are unicast addresses. And you got to think about this for a second. How many wheels does a unicycle have? One. So unicast is a conversation from one to one. So in this instance here, if we want a unicast, it will be from one device to one other device. So in this case, the 4.1 to 4.253. Broadcasts are one to all. So again, if we send it out to this 255, 255, 255, 255, 255, 255, 255, it would go to everybody. Now, broadcasts, I teach my students, broadcasts are bad. However, sometimes you have to have broadcasts on your network. So it's not, you can't totally do away with all broadcasts. But we try to limit broadcasts because of the fact that you'll notice here that when I send out a broadcast from 4.1, everybody has to look at it, at least up to layer 3. This would be going, by the way, to the broadcast MAC address also of all F. So unicast is one to one, broadcast is one to all, and multicast is one to some. And by this, you join a unicast group. And if you have joined that unicast group, you will actually process that packet that comes to you. If you don't join that unicast group, and this is typically, for instance, let's imagine that this unicast application was streaming stock data or stock, updating stock tickers on traders' computers. Only those people who are running that application would get that multicast. So it's one to some. Questions about that?
I have a question about where is it? I mean, it might be a dumb question, but the /24, where does that come from?
Okay, that's the mask. That's your subnet mask.
Okay.
So on every one of these machines, so let me do this. Let me go ahead and let me kind of build a little bit of this network. I'm not going to build all of it, but let's build just a little bit of it. Let's go and pull us a switch out. Okay, let's grab us a PC and another PC. And so on this network, you will notice that we've got 4.1/24. So on this PC, I'm gonna go ahead and connect my cables here, copper straight through. So I'm going from my Ethernet, my NIC, to just 0.1, and then I'm gonna go from here, my NIC, to 0.2. I'm gonna go to this PC and I'm gonna go to the desktop and put an IP address on it. So this particular machine has the IP address 172.16.4.1, and that /24 means that the mask is 255.255.255.0. In other words, there's 24 ones in this mask when I convert it to binary.
Oh, okay.
Okay, so that's what that means. It's shorthand so they don't have to write out 255.255.255.0. So I'm gonna click here and leave that. I'm gonna go to this other PC, and I'm gonna give it on the desktop an IP address of 172.16.4.2. Now it needs to have the same mask, 255.255.255.0. And now I should be able to go to a command prompt and an IP config. It tells me the IP address on this machine is 4.2, and I should be able to ping 172.16.4.1. And I'm able to ping from PC1 over to PC0. And see, here's the neat thing. What's this? What network is this host on? Remember we talked about how to do that? We talked about you take 172.16.4.2 and the mask, and you add the IP address to the mask to find out what network it's on. So let's take 172. So we got to convert that. Somebody convert that for me real fast. I know it's 1, 0, said 128. Be 128, be 32. Y'all convert it for me real quick. So it's 172 minus 128, which will leave us with 44. So we can't take 64 from it, but we can take 32.
Take 32. Right? Yep.
All right, which leaves us with 12.
12. So we can take 8.
16, but we can take 8.
And 4.
And 4, but not 2 and 1, because at that point we're 0. So 172 is that address, is that in binary. 16 is easy. 128, 64, 32. 16, 8, 4, 2, 1. 4 is easy. 128, 64, 32. 16, 8, 4, 2, 1. And 2 is easy. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now let's do our mask. 1, 2, 3, 4, 5, 6, 7. It's 8. 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, when we AND this, what we're going to figure out is we are on the network 101.0.11.0.0. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So we are on the network 172.16.4.0/24. And so that's why this host, PC1, can ping PC0 directly. Now watch what happens when I do this. If I go in here and I make this 172.17.4.1, watch what happens when I try to ping this now. If I try to ping 17.4.1, it's going to fail, because now these two hosts are on different networks. One of them is on 172.16.4.0. One of them is on 172.17.4.0. The only way to get between networks is with a router. So I'd actually have to have a router in here in order to route between these two. I change it back to 16, so they're on the same network. I ping 16, works like a charm. So when PC1 pings PC0, it actually goes to this process right here. It ANDs its own address to figure out where it's at, and then it ANDs the destination address to figure out where it's at.
There are concerns, obviously, about.
Okay, who had questions?
Because our kids cannot learn from home.
I had a question, and it's, you know, and I think I've got it, but a switch just allows you to just think of it as a pass through, where, you know, you're able to sort of communicate a little bit different with a router.
The switch is an aggregation device that allows us to have a bunch of hosts connected together. It is a layer 2 device. So switches do have content addressable memory table. So if I go in here and do a show, see if I can find the CAM table. Show MAC address, I can do MAC address table. Show MAC dash address table. You'll see here that this switch has learned the MAC addresses that are associated with these ports. So you'll notice it knows the MAC address of PC0. I can actually go in here and show you this. If I do an IP config /all, you'll see that the MAC address for this is 000B BE4000EE. You'll see that dynamically this switch has learned the MAC address. So what switches do is they actually learn the MAC addresses that are on them, and then can just send information from one port to another. So in other words, let's imagine we put another PC on here. So let's stick another PC on here, and we give it the IP address of, we've used 4.1, we've used 4.2, and we're going to use 4.3. Okay, so let me go ahead and put that on here, and you'll notice here in a second let's do 172.16.4.3. We're going to do 255.255.255.0. Okay. Now what happens is when I ping from PC1 to PC0, the only two machines that will actually see that are PC0 and PC1. With a switch, what the switch does is it looks at the frame that comes in and says, okay, this frame, this ping that's going from PC0 to PC1 has a destination MAC address of this 00DBD29. So let me go ahead and actually just do this. Let me do a ping in simulation mode. So let me do this. So I'm going to do a ping from here to here. You will see that in this ping, the destination IP address is 4.2, which is PC1. The destination MAC address is this 000DBD2922A2. That is PC1 that's on port 02. When this comes into the switch, what the switch does is it actually will go into the switch. The switch looks in its content addressable table and says, oh, that destination MAC address is available out port 02, and sends it only out port 02. Okay. Now, once it does that, it then will come back. And when it comes back, it says, oh, that ICMP packet coming back is destined for the host that's on port 01. And it will send it out just 01. That's what it's supposed to do. There it is. And so switches learn the MAC addresses that are on their ports and then switch the frames that come in between those different ports. So a switch is a layer 2 device because it deals with data link layer addressing, which are MAC addresses. And right here was a great example showing that. Does that help everybody? And that is a review of what we covered earlier in our section on the data link layer. Or a little bit. We actually have, as we move forward into the next class, we have an entire section on switches and on switching. And so we get a lot more in depth on how switches use their content addressable memory table and forward things based upon that table. If it's not in the table, by the way, if something comes in to a MAC address that's not in the table, or it comes into the MAC address of all Fs, it gets sent out every single port except for the one it came in on, because the switch assumes that whoever is on the same link as where it came in would have seen it. Okay. Any questions, folks? I'm actually going to stop here for the day and see if you have any other questions that you need answered. Yep. I'm going to stop.